Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video, we're going to take a look at the boundedness theorem. It's a way of eliminating certain potential roots or zeros of a polynomial function. So it says that if f of x is a polynomial function with real coefficients and is degree 1 or higher, meaning that it's not just a constant function, and that the leading coefficient is positive. So the first coefficient of the term of highest degree has to be positive. Then suppose we divide synthetically by x minus c, meaning that we're going to put c in the box, etc. If c is positive, if c is greater than 0, and you do the division and all the numbers in the bottom row are non-negative, meaning that they're either 0 or positive, then the function has no 0 that's greater than c, so we don't have to look any further in that direction. If c is less than 0, right, if c is negative, and the numbers in the bottom row alternate signs, including 0 could be treated as either positive or negative, then we know that there's f of x has no 0 that's less than that number. So it's a way of eliminating positive roots above a certain number or negative roots below a certain number. I have two examples. The first one, the function f of x is x to the fourth plus 5x squared plus 3x minus 7. It's all those coefficients are real. The degree is 4, the largest exponent we have, and the leading coefficient is 1x to the fourth. So that's positive. We're going to divide, we want to show that there's no real 0 greater than 1, meaning that we're going to divide by x minus 1. And 1 is positive, so this would go with that first scenario. What we're trying to show is that all the numbers in the bottom row are not negative. Right, let's give this one a try. Again, 1 goes in the division box. The coefficient for x to the fourth is 1. There's no x cubed term, so we put a 0 there. 5 for x squared, 3 for x, and negative 7 for the constant. Bring down the 1. 1 times 1 is 1. Total that column, 0 plus 1 is 1. So far, both positive. 1 times 1 is 1. Total the column, 5 plus 1 is 6. 1 times 6 is 6. Total the column, that's 9. 1 times 9 is 9. Total the column, and we get 2. All those numbers in the bottom row are positive, and more importantly, that means they're not negative. And that means there are no positive zeros greater than 1. Now, if, say, that 6 was a negative 6, then all bets are off, and we haven't shown anything. We know that 1 is not a 0 because the remainder was 2. So that's no good. But we know there can be no real 0 greater than 1. You could still check your rational roots that are smaller than 1, but still positive, but that's as far as we can go. The next one, we're working with a negative potential 0, negative 2. And so there, again, we're looking for these to alternate in sign. Still using the same function, so I'm going to put in negative 2, 1, 0, 5, 3, negative 7. And again, this is like we're dividing by x minus negative 2 or x plus 2. Let's give this one a try. Bring down the 1. Negative 2 times 1 is negative 2. Total the column. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. Total the column to get 9. Now notice that these are alternating in signs so far. Positive, negative, positive. Negative 2 times 9 is negative 18. 3 plus negative 18, when we total that column, we get negative 15. And we finish with negative 2 times negative 15 is positive 30. Total the column to get positive 23. So these signs are alternating. Positive, negative, positive, negative, positive. That satisfies the conditions for the boundedness theorem. By the way, if the 9 had been a 0, they still would alternate signs. It goes from being negative at -2 to not being negative at 0 to being negative at -15. So that would work as well. This tells us there are no negative zeros less than -2. So we would check other negative solutions between -2 and 0, but we know we don't have to check beyond -2. And we know -2 is not a 0 because the remainder was non-zero as well. All right, that's it for the boundedness theorem. I'll see you in the next one.